What is the Riemann hypothesis? Welcome to a journey into one of mathematics' greatest mysteries, the Riemann hypothesis. Proposed by Bernhard Riemann in 1859, this conjecture explores the behavior of the Riemann zeta function, a mathematical marvel that holds secrets about the distribution of prime numbers. It's so profound that it's one of the Clay Mathematics Institute's Millennium Prize problems, with a $1 million reward for its proof or counterexample. In this animation, we'll dive into the zeta function, its deep connection to primes, the mysterious critical line, and how this hypothesis shapes our understanding of prime number distribution. Let's get started. Introduction. The Riemann hypothesis stands as a towering challenge in mathematics, a problem that has puzzled the brightest minds for over a century. It's not just about numbers, it's about uncovering the hidden patterns that govern the primes, those fundamental building blocks of arithmetic. Let's explore why this hypothesis is so captivating. Introduction to the Riemann zeta function. At the heart of the Riemann hypothesis lies the Riemann zeta function, denoted as zeta of S. For a complex number S, it's defined as an infinite sum, the sum from n equals 1 to infinity of 1 over n to the power s. This series converges when the real part of S is greater than 1. But through a process called analytic continuation, mathematicians extend this function to the entire complex plane, except for a pole at S equals 1. This extension unveils a world of mystery, setting the stage for the Riemann hypothesis. Connection to prime numbers. Now, let's uncover a fascinating connection, the zeta function's link to prime numbers. We start with the familiar sum form of zeta of S. But there's another way to express it, through the Euler product, a product over all prime numbers p of 1 over 1 minus p to the negative s. This product form reveals that the zeta function encodes the primes within its structure. For example, for p equals 2, 3, and 5, we get terms like 1 over 1 minus 2 to the negative s, and so on. This profound relationship helps us understand the distribution of primes, a key theme in the Riemann hypothesis. Visualizing the complex plane. To understand the Riemann hypothesis, we need to explore the zeros of the zeta function in the complex plane, a space where numbers have both real and imaginary parts. The Riemann hypothesis focuses on a special line, called the critical line, where the real part of S equals 1/2. This line will play a starring role in our story. The Riemann hypothesis statement. The Riemann hypothesis makes a bold claim: all non-trivial zeros of the zeta function, that is, the values of S where zeta of S equals 0, excluding the trivial zeros at negative even integers, lie on the critical line where the real part of S is 1/2. If true, this would unlock deep insights into the behavior of prime numbers. But proving it remains one of math's greatest challenges. Visualizing the first few non-trivial zeros. Let's visualize some of these non-trivial zeros. On the critical line, at real part 1/2, the first few zeros occur at imaginary parts like 14.13, 21.02, and so on. Notice how they align perfectly on the critical line, as the Riemann hypothesis predicts. But do all non-trivial zeros follow this pattern? That's the $1 million question. Importance of the Riemann hypothesis. Why does the Riemann hypothesis matter so much? First, it would reveal precise patterns in the distribution of prime numbers, those elusive building blocks of numbers. Second, it impacts the growth of arithmetic functions, which are crucial in number theory. Third, it has surprising connections to physics and chaos theory, bridging mathematics with the natural world. And finally, it's a Clay Institute $1 million problem. A testament to its profound importance. Solving it would reshape our understanding of mathematics. Visualizing prime number distribution. Let's see how the Riemann hypothesis connects to prime numbers in action. Each prime number up to 100, 2, 3, 5, 7, and so on, marks a step in the prime counting function, pi of x, which counts how many primes are less than or equal to x. We plot pi of x, showing its step-like growth. Alongside it is the logarithmic integral, li of x, a smooth approximation for the number of primes. Notice how closely li of x follows pi of x. The Riemann hypothesis tells us that the difference between these two, the error in this approximation, has the tightest possible bound if all non-trivial zeros lie on the critical line. This connection is why the hypothesis is so pivotal for understanding primes. Explain pi, x, and li, x, in detail. To deepen our understanding, let's define these functions. First, pi of x, the prime counting function, is the sum over all primes p less than or equal to x, counting each prime as 1. For example, pi of 10 is 4, because the primes up to 10 are 2, 3, 5, and 7. Next, li of x, the logarithmic integral, is defined as the integral from 2 to x of 1 over the natural log of t, dt. This function provides a smooth estimate for pi of x, approximating the number of primes up to x. These two functions are at the core of the Riemann hypothesis's impact on prime number theory. Conclusion. And so, we conclude our exploration of the Riemann hypothesis, a profound unsolved problem that weaves together the mysteries of the zeta function, the critical line, and the distribution of prime numbers. Its solution could unlock new realms of mathematics, revealing the hidden order of the primes. Will this enigma be solved in our lifetime? Only time will tell.